Good, I can see that. I can later see that. Okay, I'm going to do the usual mistake in these sessions and try and do some live coding. So when this goes wrong, I apologize, but I think it's going to be useful to start with. So, just to say, I've lost access to the notepad. So Jaffrey, can you let me know if anything comes up there, please? This question.
Yes.
Yes. Great. So, let me just get my. Yeah, okay. So, we were looking at the end of this morning at this complex exercise. Did people get a chance to at least look over this during lunch? I realize we have some time to do exercises, but the material in the morning is kind of quite a lot. So what I propose to do now is just to go through the answers for this and take any questions people have, and then move on to the next section of content. Don't want to spend too long on this though, because there's quite a lot to get through this afternoon as well. So we were going to look at these complex, this complex class and some of the, and run the unit tests and see and fix any issues that we saw with the examples. So if I've downloaded the repository. I'm on ARCHER2. I'm just on login node 3. Is everyone able to see my window? It's a little bit bigger. It's huge for me, but I think it's a bit better for everyone else. And in this directory, I've got the complex examples. I've got complex.cpp with a long list of functions we need to edit. But more importantly, we've got a header file, and we can see in here what we discussed in the previous set of discussions. So we've got some inclusion protection. We've got a class called complex. We've got a default constructor for this. We've got some components to access the values of the class. We've got an operation which conjugates the complex numbers that the class holds. We've got a way to calculate the norm and the norm squared. That's the magnitude and the magnitude squared of the complex number. And the number of operators for comparison, and then for the arithmetic operations. Okay. And then finally, we have some private data types which allow us to actually store information about the complex itself. So from there, we also have a series of tests. And these tests are using a framework called, I think it's Catch. Let me remember. Yeah, it's Catch2. Okay. Don't worry too much about the implementation of these specific tests. We're not expecting you to understand the framework at this stage or come across this necessarily, but it's quite nice. But what it's really doing is setting a test case, requiring a bunch of things of these tests, and these have to pass. If they don't pass, then there's some form of failure, and it gets flagged in the tests. So if I just run my thing and just run make, see, I'm going to get a load of errors at the moment. I'm not even going to run the tests because there's. And the aim of the exercise is to go through, look at these errors and correct the code. As I'm going to use Vim for this. And add in. Just for sort of speed more than anything, I am going to just enter these quickly. Sort of highlight any major issues that you might expect. Just checking what I've got here is the right thing. Yeah, so definition of, okay, right. So here we've got the function. So basically we've got all the functions here we have that we listed before with various implementations of them. Some of them are correct, but there's also some things that are missing. Key things that are missing are the constructors for complex class. We need to introduce those first before we do anything. So we need a complex, if we want to initiate with a real value only. So then we have some initializer list. If we paste this real into the private member RE. Okay, that's one thing that's missing. We also need a complex, we need a constructor that's complex for if we have both real and imaginary part. Yeah, and we use the initializer list for this. So we had a number of issues with constructors. We'll look at anything else, if that's helped. Let's put it in this first. So we still have some more issues. We'll have them now in the real class and in the pretty good some other places. Still got some work to do. If we even get some compilation. So going through my list here, what else is obviously incorrect? Let's just check. I instantly managed to get a typo. That's fantastic for me. Yep. Thank you very much. This is the perennial danger we're trying to code things live. We still have some errors though. The return type of the initializer list is an error. So in function complex operator, but we should start at the top of this. So no definition matches complex, complex real. Check. Yeah, so we need actually a definition. So I jumped the gun a little bit here, and what we likely need. Check what I'm going to be doing here. Yeah. Okay. Okay. We also need to define it here also for the real and imaginary case. As you know, of course I have. Okay. Do some of our errors a bit better than just misspelling everything. So we have no declaration matches const double. Okay, grab by reference and have no declaration that matches a const version of the conjugate function either. So we need to check those are. So we have a version of this here that does not need the const keyword on this side. Here. Now on conjugate, const here. I'm going to see what we get. Then it's an issue with curly braces in conjugate. They're fine. This is a different way of defining them in the initializer list for complex. Because all you're doing here is saying, I have a different, yeah, I think the problem is in the HPP file, but going back to the curly braces, this is valid. It's just a different way of doing the initializer list for real and imaginary. And all you're doing here is saying, I know I need a new object, which is the same as the old one, but they're reversed, so that's fine.
Just
Jeffrey, yeah?
Yeah, just the declaration differs from the definition. The const keyword after that.
Yeah, exactly. Yeah. Right, that at least compiles. We're downloading ARCHER2, and it's trying to build tests out. And of course, it's going to break on something. It's not produce tests. Undefined reference to operator minus. Okay, so this is operator minus. Let's check that's actually been. So let's see actually. Not have a particular definition of this function. So let's check. So I was looking at the wrong one in here. We do have it defined here. So we just need to add one in. Differences here. Okay. Okay, can we run tests now? Yes, and we're getting failing tests as we expect. So now, while things are compiling, we still see errors in particular examples that are failing the tests that we've set up. So that kind of gets you some of the way there. I'm going to quickly just go through the last few bits. I'm just worried about time a little bit because we spend more on this than I was hoping to. But some of these kind of issues are obvious once we have a little look up in the code here. So let's just go back to that. And where do we need to focus? So we can, the advantage of test frameworks, they allow you to tell you where you should look at. So complex numbers can be compared. So there's an issue in comparison. Complex numbers can be conjugated. So there's an issue in conjugate. But this is also using comparison. So we have to be careful. Again, these are all looking at, they're using comparison. So we should start off by looking at comparison before we do anything else. And if we look here, we have a complex const A and a complex const B, and returning a statement of truth, a Boolean, based on comparing real to real and then imaginary to real. So we're not actually have a correct definition of how we do comparison. So if we update that first, Actually, I should make clean because I don't trust make sometimes. Wait a second. Right. Okay, so see that was actually a few of our issues there. Were in the fact we had a problem with comparison, not the rest of the problem with the test that we had a problem with the fact that the way we were testing, not actually the function that the test was trying to test, if that makes sense. Okay, and then finally, complex numbers can be multiplied. So this is at CPP86. So we are comparing the guys. Let's look at tests. 186. Looking at Z equal to I. So for complex, if we make Z complex and give it 1, so it's only got a real value, it doesn't have imaginary part as well. And we compare that, we multiply it by I, then we should say, which is Z, and then make that equal to Z, then Z should equal to I. Which makes sense, because if we multiply through by 1, we should just get I back out. Okay. So, yeah, because we haven't defined how we should do multiplication of complex numbers. For speed, I'm just going to copy and paste this in for now, but logic is defined there for you about how to multiply complex numbers together, and therefore this should make sense in terms of what we're trying to return here. We're going to return a new complex where we've worked out how to determine the real parts and the imaginary part of the resulting complex number once multiplied. The two numbers are multiplied together. And then we're returning that new complex. That's then used in the comparison here to give us our result. Okay, and then that is all the issues with that example, and that those set of tests now pass. So that was kind of the key to that example. It's really like about analyzing the code you're given, noticing around the fact that the comparison operator is key to most of the examples, and if you don't see that and pick that issue up, you're going to get a lot of false positives in your other tests. Okay. Having gone through that, did I have a... We are now going to discuss containers as advertised earlier. I think I want access to this later. Okay, so we're going to discuss loops, containers, loops, and iterators in this session until about, I think we said 3 o'clock. To check without flashing my email to everyone. So what are containers? We have some intuition about what this should really mean. In C++, a container holds an object of uniform type. It only objects that it contains and provides access to its elements. This means the process of accessing and the performance of these operations depend on the container itself. Okay. So the standard library has a number of containers, and these are template classes, and we'll come on to templates tomorrow. But the main ones we're going to touch on is vector. This is a dynamically sized contiguous array. An array, a statically sized contiguous array. So dynamically means happens at runtime, statically means happens at compile time. A list or a forward list, a doubly or singly linked list, and then we have a ordered or unordered set and an unordered or ordered map. So In the vector, so like I said, the size of this is determined at runtime, hence the memory is allocated at runtime. The elements are continuous in memory, so that means it's fast to jump from any element by index and to iterate through. Is this like a data structure in Python? I'm trying to remember the exact data structure in Python. In a sense, but you should wary about direct Python comparisons, because while they may have similar structures, and underneath what's happening in Python could very well just be this exact vector. I don't want to draw too heavily on that. Let me just look this up quickly so I can answer your question fully. Way, yes, but the access pattern may be different, and there's a set of yeah, you could think of it that way, but I would be careful to draw too many conclusions from your Python standing onto this, because I think this will likely give you more fine-grained control about how you do accessing and be a bit more rigorous with certain things than Python is. Okay, so you can use this to sort of simply sort of a number of data elements in a container together. And in this example piece of code here, we include the vector library and IO stream. So the vector library allows us to get access to the standard vector. In this case, those angle brackets mean there's a template parameter which allows us to put any type in there, so that the vector is a vector of integers. And the member is data, and it's going to get initialized by getData function. And this can be anything. Now, if I prepped myself correctly, I should now have an example piece of code I can show you of this. Right. What did I just do? Show it. Okay, this is just some simple implementation of that get data, where I've just said I'm going to have a vector of ints. I'm just going to return it, and it's going to, and I need to make this bigger for you because it's probably impossible to see right now. Okay, you have this get data is going to return some vector of ints. That's going to fill this initial data member. We're then going to loop through data and print the output. And at the bottom, I'm just going to run show data. Okay. I've compiled this, and then I can just print out. And as it's printing multiple times, and there's an end L there, it's going to do it on a new line. Okay, it's the simplest sort of example of this show data. It's actually doing. Okay, I think I've got end L and I've got a slash new line, but it does the same thing, in fact. So the key thing here is that the data locality, and this is the key thing about vector, is that this is contiguous, wins over algorithmic complexity. That means that if the data is local to one another and it's close to in caches, then it's going to be much faster to access, and therefore you're going to be a better performance by looking at continuously stored data. Okay, so what are the sort of supports? What are the things you can do, the vectors have? So we can do copy and move. You have random element access by index, which means you can index the vector and grab a given element. You can resize this, and you can do pre-reserving of memory if you know what the size is going to be before you add the data into it. You can insert elements, you can delete elements. So the vector owns its elements. So when it reaches the end of its lifetime, it has a destructor, and that's going to destroy it and destroy the elements that it owns. So this is nice because it means that it cleans up for you, but if it goes out of scope, then it is going to delete the things it has ownership over. And beware that if you do resizing, you're going to force allocation and copying, so that you may have to be moved around, and that can be quite costly. So be careful about how much you do that. Okay. So we can look at another example here where we can try and build a list of primes, and we have a function called firstNprimes that returns a vector of unsigned int, because the assumption is that all the prime numbers are positive that you're going to return. You have a member of this function scope called answer, which is just a vector of the unsigned that's going to be returned. You have an unsigned int, maybe prime, that equals 2, which is where you're going to start, and then a while loop that says, as long as the answer size is below n, the number of primes that we're going to look for, we're going to test the, if this is going to be, if the number we're looking at is going to be a prime number, and if it is, we're going to add that particular number onto our answer vector using pushback. So this is dynamically being done and growing the length of the vector, and then we're going to increment the value that could be a prime. So then we're going to go up, so the next test will be 3, 4, and we're going to keep testing. So to show you an example of that, which is going to helpfully not want to load on me. No, it is. Yeah. Here, all I've done is taken the example code we had on the slide in this function. I'm just passing this into, basically this is a modified version of the previous example I've just shown you. So I have some vector, I'm just going to show some data from getData, because in this case, instead of getting the data just as a random list that I've provided of a random array of values I've provided, I'm going to get it from first primes instead. I'm going to look at the first 10 prime numbers. I've got some function that does the test of whether this is a prime number or not. I've just grabbed, and then I'm going to show the data, because that's going to print the data out for me. Okay, and then the results of this look like the first sort of 10 primes that's being calculated. But this is kind of nice because you can show how you can build on your previous, the previous example. Okay, some of that is probably duplication. I don't need to get the data if I'm also producing the data, but it's quite useful to see how these quickly stack using the same data type. Right. So we've talked about vector. Now let's talk about array. So it's contiguous in memory, but the size is fixed at compile time. So basically, it's like a vector, but you can't change the size. Its only difference is in its construction. The list of values inside the braces. So you see here you are using grid point. This is a, I think we discussed earlier, you might have a using keyword to say, we're going to say this is an equivalent type. And instead of vector, just int, you've also got a size that the compiler is going to take. And again, these are both can be used as templating arguments. We'll discuss that in more detail tomorrow. And then we can print these values out. So we can print out the size and it will just return 3. Okay. So list and forward list. These are almost always implemented as doubly linked lists, unless it's forward list and that's singly linked. Elements are allocated one by one on the heap at runtime, Traversal requires following the pointer from one end. You get fast element insertion if you don't have to look for the element. Okay. If you're trying to design things where you're adding and removing the ends a lot, or of the contained objects, but the contained objects are expensive to move, then this allows you to add things but just point where they are in memory, opposed to having to move them to a contiguous region. Consider converting this to a vector with a different access pattern. So the forward versus the standard, so doubly or singly linked list, it's just whether you can traverse this in both directions or one direction. Are vectors larger in memory? I want to say slightly because often what you'll see in the definition of standard vector, I think, is that it's wrapping an array, but I couldn't say anything definitively without going and checking documentation. That's lists. We also have sets and map. Okay, these are associative containers implemented as sort of data structures for rapid searching. So you have some form of tree structure inside that you need to cover. They're quite useful there. So a set is just a set of keys. A map is a set of key value pairs. The types between the key and the value can differ. You must have a defined comparison function for the key, so you can Oh, I did cut it out. Sorry. Is there any advantage of using an array over a vector? Pilot will know more information at compile time, so it might be able to do more optimizations, and if you're doing anything dynamically, it's probably the most obvious thing I can think of. But I don't think there's anything that you're really going to miss by using vector. Vector is often the kind of the standard container you default to. It's good to know that array is available, because that's what you're probably more familiar if you're coming from a C background. Okay, going back to sets and maps. So say a set is a set of keys, and you have also maps, which is a set of key value pairs. You must define the comparison function for the key type. Otherwise, you have no way of knowing whether you have found the key you were looking for, and therefore its associated value. You may want to use the unordered version, which uses a hash table and requires a hash function, because this can be quite efficient. If you either have a large key space that mostly lacks values, or we'll be looking at unpredictable values for a lot of frequency, adding and removing values, these can be quite useful. So you may want to do unordered versions of these. Okay. So we can discuss a map example. So in this diagram here, the idea is we're looking at some form of fluid dynamics code, which is modeling in a mesh the boundaries of an aircraft, the geometry of an aircraft, and is going to pass information between the different regions. So different processes are controlling different colored regions of this mesh, and those processes have to communicate when they need to pass information between the different processes in order to progress the simulation. Those of you familiar with MPI, this will be an MPI type communication. Okay, and that's the example we're going to look at. So, not in a lot of detail, but this is why this can be quite valuable to have a map. So, after starting all the processes and reading the domains that we've assigned each process, you might have some code like this that says, I'm going to have a map between an integer, which is the key, and some boundary communicator, which is the value, which tells me how I'm communicating over boundaries. In these type of examples, there is a list of processes. Each process is given a value called a rank, and those are unique to that process. And the MPI size value here in capitals is a value that's set, that is the size of the total number of ranks, basically. So we're going to go through the ranks, and we're going to test whether these two ranks share a boundary. Do I share a boundary with rank P? Okay, and if I share a boundary with rank P, I'm going to add a value to my ranked comms map, and that is going to be the value of the rank I have a boundary with, and then the boundary communicator, the methodology for which I'm going to communicate between my rank and rank P. And that means that I have a mapping to know how I'm going to do communication in the future. So later on in my code, when I need to do some form of communication, I can go through and say, go through every member in this list of communicators I have, and I now know where I need to send my local data to, because I can know which ones I'm going to access as I go through this mapping. And this is going to be quite nice to associate those sort of lookup tables in your code. Okay. The guidelines. Each container has its traits. They define the place where they are great. Particularly vector. You don't need a lecture. Just use vector. Okay. Just use vector is a default, and if you need some extra functionality, or think another one might be useful, then you use that carefully and consider it carefully. But if you're in doubt, vector is usually a good choice. Okay. So that kind of covers an introduction to containers. During the next exercise, we'll look at playing around with a few of the ideas of containers and a couple of examples, including maps and vectors. So there won't be, we'll do an exercise of that in a moment. Loops. In C++, there are three types of loops. You have a while loop, a range-based loop, for loop, a C-star for loop. Okay. So while Boolean expression true, you execute the code. Okay, very simple. You've seen this before in multiple contexts, I'm sure. So, in this example that we saw in terms of print first primes, yes, this is what we used here, right? We did, while this condition is true, keep adding until we've hit the number of primes, the size has hit the number of primes we expect to output, and therefore stop the while loop and then return the answer. That's the usual way about you'll end up using these loops. I have range-based for loops. Okay, that's based on, it says, show the data, and we saw this earlier as well, for an int x, which is for the members of data, the vector, we're going to print x's. So for every int inside the container, we're going to print. And this is nice because you have a range is based on the object which you are data, and therefore you don't need to define this or look this up. It has the information necessary to do this. You can also use this thing to do things like double in place. So here you see the interesting difference is the reference, whereas before you were just getting the value x of data. So this ampersand here, discussed earlier, is a reference. So into the function show data, we're passing a reference to a reference. We're getting the reference of whatever is input in the function call. We're calling it data, and then we're going to go through this element by element. In the double in place example is when we return. It's void. We're not returning anything, but when we finish, we want to have updated the values in data. So instead of we're taking, we're now going to take a reference to each x in data and then update it. And that means that when we finish and we return double in place, we actually get a change in the values inside data that is held by the scope that this function is called within. So the point here is really the fact that this can be used to modify things that live outside this scope. So you can iterate over here with anything that has a beginning and end member functions. All STL containers have beginning and end member functions. And you can also have any types where you have overloads of the free the free functions begin and end, accepting your object. Okay. So we'll come back to that in a minute, but we also have C-style for loops as well. Fortran programmers will know this is a do loop. So instead we double in place by going through the vector, but we know its size because we're looking up its size here in the for. So we have some int I, we initialize it to 0, and have to set it to 0, but that's quite common. The condition needs to be met for this to finish is that I is no longer less than the size of data, and then we're going to increment I. And then we can multiply data values at each point by itself, sorry, by 2, and then set it equal to itself. Doing the same as we just saw, but it's a little bit more verbose. Instead, so what were you talking about beginning of functions? So it's a question here. We'll come on to that. There's a slide in a moment that compares this, and it's kind of down to your compiler is the answer, and what optimizations you do. So what is an iterator? So if we think about a C-style for loop, and instead we can have iterators, and this is kind of the old-fashioned C++ style for. So now instead of a int I that we're going to increment, we have some the member of type of the vector, which is an iterator it, and we're going to give its value begin, so the beginning the way through the vector, and it's going to test whether it's a hit end, and then we're going to pre-increment it as we go through. Then to use it, this pointer points to values inside the vector, and we're going to dereference it with the star. So instead of the pointer, we're going to get the value that it points at, and then we're going to multiply it by 2 and update. Okay, that's kind of the way you can use iterators of for loops. And then the syntax can be changed, so this is slightly nicer. Because I know that data.begin has type iterator, because that's what it's been defined to be, I don't need to explicitly state it. I can use auto, and it will work it out for me. Let the compiler deduce that. It just makes it a bit cleaner, but it's essentially doing the same thing. Okay, you can implement your own iterators. So to define your own iterator, you need to create a type, several operator overloads. Exactly which ones depend on the category of iterator you need. So the basics are dereference operator. You need to be able to get the value to either read or write from the iterator. Okay, so you need to be able to get the values they're pointing at. You need to be able to pre-increment. You have to be able to go to the next one. You need to be able to bind it to a name. And you need to be able to do some form of inequality comparison. You need to know when you're done and finished at the end. Okay. So we have got until 40 minutes now to look at an exercise. In this exercise, you can claim the repository as you've done before, so you should already have access to the files. And we are looking at a set of tests in the same structure using ARCHER2 as I've just gone through. I will answer your question in a moment, then I'll just finish this explanation of what we're going to look at. So again, test CPP holds some basic unit tests. Have a look in there to understand what you're being asked to do. Vector ex.cpp and .hpp hold some functions that work on standard vector, provide their implementations. There's some information in there about what you need to provide. The tests also require you implement a new header, a pair of files, a function that adds a string to a standard map as a key, and the value being the length of that string itself. Okay, so you're going to have some form of key value pair there based on strings and their size. You can find the documentation for map at cppreference.com. This is an excellent resource. Getting used to searching through this is very good. And you can compile this with make as before. Okay, so if I find my right tab, so here we have contain. Okay, yeah, so I'm not going to do this here yet, but let's give everyone 30 minutes at 10 to 3 to have a look through this. And then I'll come back just before we have coffee and discuss the solution to this. But try this yourselves. I'm here, Jaffrey's here. Please ask any questions in the chat as you go through or have any issues, and we will help you. Just before we go off to do that, Ben W. I've come across iterators before, but never found a good explanation. Are they just some object that you access another object with some certain stride? Kind of, yes. And the example we will look at later will give you a better way to think about this. So the modern ordering example will allow you to think about other uses. So I'll defer that till then. I think that'll be good to go through before discussing this question. Okay, half an hour now. Send any questions into the chat. I'm just going to stop sharing my screen for a moment. So just to clarify here, that you're given the bones or the correct bits of vector underscore x CPP and vector underscore x HPP. Okay, what you're being asked to do is provide a map, additional files called map underscore x CPP and map underscore ex HPP in addition. So they're not a conversion of the vector ones, they're not a duplication of them, they are something else. So have a think about what the tests are asking for and what the functions the test is trying to call. For example, there is a section at the bottom that specifically of the test.cpp file that specifically looks at test case map adding. Okay, it's using word len something. It's calling certain functions like add word. That need a certain set of properties that these tests are helping to define for you. So the exercise is about reading through this set of tests here and thinking about what you need to add in to make sure you satisfy these conditions. Okay then, so let's just quickly go through this example. Just share my screen again. Right. Okay, there. Oh. Right, can everyone, Jeffrey, can you hear me and can you see my screen?
Yes, I can hear you and I can see your screen.
Fantastic. Right. People shout if suddenly you can't. So the aim of this exercise was to add to so this directory. We've got some instructions in Markdown you can look at, which is the same as on the slide. I know the repos are slightly different names, but change that slightly, but you're looking at vector CPP and vector HPP. There are some functions that work on a vector. We need to provide some implementations for those. The tests require that you also implement a new header implementation file pair, so a HPP file and a .cpp file, and functions to add a string to a standard map as the key and the value that is the length of the string as a key value pair. You can find documentation on map on this reference, and I posted the exact page on the in the chat, and you can compile with make to make your life a bit easier. So initially, if we look at vector CPP, sorry, I meant to say vector HPP, I think we messed up. We have two functions. We have a get even, which is just get the even, just taking a vector, sorry, it's going to return a vector of integers, and it takes a vector of integers. It's going to return a new vector which only contains even elements of the input vector. And secondly, you want a print vector of integers, which is going to print this data to a string. Okay. So you just copy this, and it's given, the interesting thing here, it's given us a format that it's expecting to be correct in the vector printing method. So the first thing we need to do is look at our tests. We're trying to conform to, and it's got some type aliasing in terms of how it's defining a vector. So IV is meant to be an integer vector, just to confuse that slightly. And then we have a int range, which is returns a type of integer vector. It's part of the tests. And now we have some tests which look at is the output vector even here, and then it has some tests of the testing code, and then it gives you some examples of what it's to test on. And then it has something that's testing and printing. Most of this is around making sure the formatting is correct, that it does the things that it's kind of required. I think this example is a little bit pedantic, but it's quite good to get you to understand this sort of loop, iterating loop around development and having a testing framework which does define what you're expecting the output to look like. And then separately, we'll come on to the tests around map. So we need to edit two functions and give them implementations. So we don't have in here, it's the standard, it's the print example. So initially we need a sorry, I've got maybe right, we need some output vector, which we're going to do auto because we're going to set this equal to standard vector of integers, because we've been told that's what it needs to output, and we're specifying that with any values initially, and that's just going to be a container for receiving outputs we're going to put in it. So then we're going to have a for loop. We're going to use auto ampersand to make sure we retain the constantness of this, and we're going to get element of this from source, which is the input. Okay, and then so for every element in source, we are going to check if that element has a remainder is divisible by 2. Let's check if it's even. And if it is, then we are going to push the resulting value of that particular element within source onto our answer, and then we are going to return our answer. Okay. That is what we need for that now. Is that going to be enough to make any test work? I think it's still going to complain us. Yeah, it still complains we need a map. Okay, let's finish this and then we'll add the map examples in. So for the print case, we've got some output stream that we're going to add to called output, and it's to pass by reference. So which means that when we test, we're going to flush that output stream so we can add to output, and it's going to persist after the life after this scope. So this function. So we're going to do output, and we are going to put a beginning brace, and we're going to have a space here. We're going to have a bool, the first element. So that equals true. Okay. And then for each of the elements, we're going to pass by reference, by a constant reference from data, because it's put up there. There's x in this for loop. Test if this is the first member, is first true. And this is all for formatting, okay? So this means for the first element, sorry, after the first element, we're going to always add a comma. And then after that, we're going to set first, let's get my for loop. So I'm going to run into the for loop. It's not going to work at all. First equal to false. And then we are going to output the current element in data x into the output. And we're going to go all the way through the vector, and then we're finally going to put the closing brace for the formatting of the output. Okay, so that's what we needed to do for the vector part. Okay, for the okay, so Morris discussed this earlier. So why the question is confused with double ampersand and in the for loop. Why double and in the first? No. This is around we have these different layers of there was 3 layers around whether how you're using auto and constness. You either just pass auto and you didn't preserve the constness, you provide auto with double ampersand, and then you inherit the constness of each element or the elements of the vector. So in the top case, you're saying I'm going to be as const as source for each of the elements. And in the bottom one, I'm saying I'm going to ignore the constness of data and I'm going to make sure it's constant because I know I'm not editing this here. Whereas, so you can, you're just printing, so you're not going to edit anything, so I can show that's constant. But where I am making and pushing elements back onto answer, I may want to preserve the constness as if they were source. I think you could probably double ampersand maybe overkill in the first example, but that's kind of the answer in this in the slides in the classes section. If you want to review those. Okay. So we also need to provide some map functions here as well. So let's look at what test again is example. Now we've done the vector part. What functions is test calling? So test is calling something called add word. Okay, we've not defined that anywhere else. So we're going to need something that looks like that. So also we have this using word to len is the definition of a type we're going to use. So it was actually pointing out as a standard map of a standard string and an int. So when we were asked in what we were going to implement, we were told we needed to pass a string in as a key and have an integer as its value, which was the length of that very string. So we need some way to calculate the length of the string and pass it in. So here, when we're doing the tests, we are taking one of these words and we're making an example one. Testing whether it did it correctly insert by looking at the return status and then making a requirement in the tests that it does. And then we're checking that this number of elements then after we've done one insertion is 1. And we find that we need to check whether the test is not, if we try and look for test, the return of find is the iterator of the map. And if it fails to find test, it just returns the end of the end iterator of the map. So you're trying to check that it's not gone all the way through, found nothing, got to the end, which means it would have not inserted correctly. The other requirement of this implementation was that it only inserts once. So then the second test must return false, so it must not have inserted if you try and add it again. So the result of trying to insert for a second time should return, but by running AdWords should return false. I did not insert because you've given me a duplicate value, and I've checked that this value didn't exist before I tried to add it. The requirement then is testing that. You're trying to check that this did not change the size of the map because the second insertion didn't happen, and you're trying to check that again there is a single value of test and it is not the end of the iterator. The other good thing that's kind of missing here is that you could add as a test to say is the length being correctly added and calculated from the example. Okay, that kind of helps us define what sort of things we're going to look to implement inside these two new functions, but let's actually write them. Sorry, this new function and these new header files. So we need vim map underscore ex dot HPP. I can even spell much more helpful. So again, we're using include guard to begin with. If defined cpp ex underscore map underscore ex underscore HPP. If it's not defined, then define it. Then we want to do end if. Okay. So we need to use include map. We're going to include IO stream because we always include IO stream. Some print things. Right. In the example answer, we're using word to len as is done in the tests. It's not strictly necessary. It's a nice shortening, but I often find that too much using and redefinition of types can get quite confusing about what's actually happening and obscure what you're doing. It can be nice if these types get very long, but just be careful about readability of your code if you use them everywhere. Definitely, we're going to want a bool returning to know the status of whether we've added the word, and this was the function that's being called to add words to a map in the example tests. And here we want something we can update, so it must take a reference. These maps that's a string and an integer. Okay, and we're going to also need to take in the map itself, and all we otherwise need is just the string. Okay, and this is, we don't want to be editing this at all, so we can do a constant reference to it. Right, that should be enough what we need in the header file. I'm just going to check I've not made any obvious errors here. I don't think so. I'm sure we'll find some shortly. Right. CPP file. So, first of all, thing we need to do, we need to include the header. Because the header is also included in test. This is what it's expecting. It's expecting to include the header. And then we're going to, I have another way around. We need to include the header here to do the implementation. So what we're going to have is what we've just defined in the header, which is a bool of words len, which has a reference to words len, and a string of a word. Now, there's different ways of doing this, and I actually use a different function than is suggested here, but I'll take the defined answers. So we can have auto, and we can have iterator that's being returned. And if you look in the documentation, we can search through the map using find. And this is a function built into the map that looks for the word that we are going to potentially add. We are then going to test to see is if this iterator is equal to the end of the end of the map, then we know it's not already inside the map itself, so we can add it. And to do that, we just pass in the key, and so they're equal to the value, and we can get the value by doing word.size. Okay, and then we need to know we return we know we said the bool, this is going to return a bool, and if we've added in it successfully, we return status. So we can know if this is what we expect it to do. Otherwise, we've tested whether it's already in there, and if it's already in there, then we don't add it again. We return false. Okay, and we just going to make clean, make and see where our errors come in. Of course, I've got an error somewhere. Well, let's not go and skip. CPP. Probably typoed something. Trying to spell. Okay. That seems to be building all the tests. If it's taking a little bit of time, let me think about this. Okay, and that's passed everything. So that's implemented what we kind of wanted it to do. And you can see there how we can use information about iterators and the construction of loops in order to operate on containers and use containers for certain functionality. Right, any questions at this stage? I take the deafening silence to mean everyone needs a cup of tea. We'll start again at 3:30. Okay, and we'll look at Morton ordering. What will likely, sorry, not Morton ordering, that's the example. We will look at resource management for an hour, and then we will stop at 4:30. And what we will likely do is I will leave you with the exercise at 4:30 to look at, so we have enough time, and we will come back to it tomorrow morning and look at what the answers are meant to be then. Okay, so see you all at 3:30. Show my example of will it throw an exception if I just try and manually put? Oh, you're getting fun errors, are you? Okay, right. Do they just throw kind of makes the example more void if it does, because it should just throw an error then. It doesn't seem like it will throw an error from just a quick Google, but I will have to. As much as I trust Stack Overflow, I don't trust it. I mean, the easiest thing to do is run a couple of tests. This is exactly this sort of question is take just a new main function, set a map, add 2 keys to it, and see what it returns to you. Often that is the simplest way to answer these type of questions. So I think it replaces. Not going to necessarily throw an error. So you both got this error. That sounds like a fun one. Seems to be in catch opposed to. Okay. Sorry, people who were looking at that. Okay, so yeah, we are going up if I may include. Blah, 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 blah. Can someone post their code that is causing that error? Because it's definitely erroring everywhere. The other thing it could be is if you try a different compiler. You what were you using? You should be able to do something along the lines. Yeah, did you load yeah, did you load GCC module that we discussed earlier? I think people may have logged back in after lunch and not done this, so that you've got GCC 12 loaded. Oh, you're in your local machine. Yeah, in that case, I don't know what to recommend, because that's the same person who's having the issue. It might depend on the version of G++ you've got, GCC you're using. I think I'm using 11.2. It might just be a compatibility thing. Okay. Jaffrey, do you mind having a look into that while I take 5 minutes before the next session?
Yes, I'll check.
Thanks. There might just be a documentation about catch that has an error with a. Are you all Mac users? Is the next question I like to ask in these situations. Yes. Yeah. Okay. Have you set up ARCHER2 accounts? Because the easiest and quickest thing will just be to log in there and do this. You don't need to submit jobs. This stuff is lined enough way just to sit on the login nodes with everything else. Yeah, please. Thank you very much. Right, back in 5 minutes.
So this error seems to be in the Mac version. So there has been an issue, same issue put in the CPP GitHub page, and this error seems to have been fixed. And maybe trying the new catch.hpp version might help, I think.
Yeah, it might just be the make file is updating. That's great. Thanks. Okay, last hour today. We'll start by talking about research. Okay, so that worked. Good. Okay. Well, sorry. We'll start by talking about. I'll share my screen. Resource management. And things a little bit. So we're going to resource management. A few things about pointers. And a little bit about some patterns that are quite common in C++. So again, jumping in with any questions you might have during this session, and at the end, we're going to go through an example on Morton ordering, and that will take us till the end of today. So we'll probably finish possibly a little bit early, depending on how fast I get through these slides, but we'll see how we go. Just check that my sound to run through as we get through this. Okay, so in a program, you often need to manage resources. Okay, so this can be a number of things, but some kind of obvious ones that in computer science would be memory, files, GPUs, network sockets, things like that. So these are all kind of like, they're not all physical, but they're resources or access to something that you need to manage. Okay. So memory. So OSs give processes a flat address space. Each byte can be accessed by its address, which is just a number. For most purposes, it's considered two parts: stack and the heap. So the stack is so in C++ and C and many other compiled language, local variables are stored in the stack frame. As your program runs, the local variables that are defined get space allocated by the compiler relative to the current stack frame. Each time you call a function, you start a new stack frame by incrementing the stack pointer. Variables are implemented as offsets from the stack pointer, so allocating a local variable has no runtime cost. When you return from a function, the stack pointer is updated, and deallocation also has no cost. These allocations are called static because they have been prepared at compile time. Okay, this is really important. The heap, on the other hand, the OS makes available some memory for dynamic allocation, and that's the heap. You need to request some memory, store an object, and give it back when you're finished. Okay, and that's allocation dynamically. In C++, you can get a pointer to an object using AND. So AND is the address of operator. Okay, we've used this seen this in terms of references to things, but it is the address of something. So when we have, okay, and then you can also read the value that is pointed to by a pointer by using star, which is the dereferencing operator. Okay, and that says, I've got a pointer, please pass through this pointer and tell me the value underneath it, and then act on the value I am pointing at, the memory location I'm pointing at, not the pointer which holds an address. Okay, so in this little example here, we've got same here, yes. We have got an int I, which we set to 99. Okay, no pointers, no references, nothing to do with that. That's just an integer I, which is set to some value. We then have a integer, which is a pointer. So we have an integer pointer type, I underscore pointer. Okay, that is a pointer. It stores the value of the address of I. So it's kind of like the at. You can think of Amazon a bit like at. That, what is the address at which I is at? And that is stored by I pointer. Therefore, we can use this pointer now and dereference it using star to get its underlying value. Okay, and that will give us, we can able to increment that, and then we can print it. So a quick question: would auto I pointer equal? Oh, blimey. I don't know is the answer whether that works or bad practice. Especially when it comes to pointers, I wouldn't want to trust auto. It should know what it's doing, but you should be kind of avoiding pointers as much as possible, I think generally they're included here for completeness and also to make sure you're aware of them. But the issue is that you can point to memory that's invalid, and we'll come on to that in a second. But you want to be, my point is that syntactically, you want to be explicit about what the pointer is, and you don't want to kind of leave it up for the compiler to interpret it something else, because the reference value might be a perfectly valid, things are perfectly valid other type, and it may just get interpreted to something else that's not explicitly a pointer. Okay, anyway, the example we have here, I just have in this piece of code, right? So it's exactly the same as root to sin. Then I compile this into just test, and you can see this returns 100. So if I just cat out an example, to review this, we've got some integer I 99. We make a pointer called I pointer. This die is just part of the type. We set that equal to the address of our integer I using the and we then dereference our pointer so that we get the value that's stored where the pointer is looking at, and we increment that location's value. So that 99 now becomes 100, and then we print it out. And then our result from running that test gives us 100. So you can see that we've pointed at our location and we've incremented something, and the value's been changed, even though the print statement has nothing to do with the pointer, it's everything to do with I itself. So that demonstrates we've accessed information using our pointer. Okay. So pointers are a lot like references, but they're not guaranteed to be initialized to a valid value, and this is very important. And this is where you get into a lot of trouble with pointers. It's valid to assign an arbitrary value to a pointer, but actually using it is undefined behavior. Okay. Typically it crashes, but what's more likely and much more dangerous is you get some silent corruption of data. So here you're saying I'm going to set the as a pointer I pointer to a hex called dead beef, and then I'm going to try and increment some random location in my code in the system. I have no idea where that address is, if it's valid, if it's not, if it's good. So that's just bad. We don't want to be incrementing random bits of data across the system. And this is where pointers become, they're very useful and powerful, but also very dangerous if you're not careful with them, because you start editing potentially invalid sections of your program. So use them with great caution. Okay. So returning a pointer from a function where the pointer is a local, is pointing at what was a local variable inside the function, is a recipe for a huge problem. Why is this going to cause a problem? Because as soon as that function goes out of executes and finishes, I goes out of scope, potentially is cleaned up, and the value that's being pointed at to is now maybe reused, or the address being maybe used for something else, may still have the correct value, is undefined. You've got no control over that because the local value existed in the scope of the function. So don't do this. Okay, don't use pointers to pass things around. What would have been better is to actually there's no caveat, just don't do that. Okay. So in C++, you can manually create instances of an object dynamically with the new command, and that will make you a new pointer to them. But try to remember to destroy them with delete. Sorry, command a keyword. But doing so is a recipe for problems, because you have to control and make sure that you do the bookkeeping here. And humans are notorious for forgetting to do this, and that's not a good plan. You can leave things left over or not clean up after yourself. This can lead to running out of memory or other issues in your code. So try not to resist the urge to just new and delete things. What would be better is if we were to use the built-in functions of objects to do this tidying up for us. So the destructor can control what happens when your object reaches the end of their lifetime or the end of a particular scope in which they're defined. This is deterministic. So when the local variable goes out of scope, when an object that contains these values is destroyed. So so like a container. If a vector was contained a bunch of objects, when that vector was destroyed, the objects contained within it are also destroyed, and therefore you have got a smooth way to exit. When the programmer, say, asks calls delete on them, then the destructor will be called. For a class called name, the destructor is declared like this: struct of name, and there is a function called tilde name. Okay, and that's the destructor. So it's important, you should never call this directly. The compiler will call it for you when the objects are deallocated, all right? But the point is that when you hit the end of a region of curly braces, the end of the scope, it will be called. A very important pattern in C++ is resource allocation is instantiation. This is also known as constructor acquires a resource, destructor releases the resource. What it's trying to communicate is that any resource should have a lifetime tied to an object. That means that when the object goes out of scope, then the resource is released. So that means that most commonly this is memory, but you don't want programs holding on to certain resources beyond their lifetime. And you can be careful with this if you follow. Sorry, you can make sure this happens if you follow by this idiom. So we have an example, and the level of which I'm going to program this in front of you is questionable. So this is an example of vector. Okay, it is a vector of doubles. So I think I will. So my array has a size which is an unsigned integer because your size can't be negative. And we set the data member equal to 0. It's a class, so everything is assumed to be private, so the size is private. And then we have a pointer of doubles called data. And we initialize it, we give it a value of null pointer to begin with. We have the default constructor, okay, which is default, and then we have an explicit constructor which takes an unsigned integer n. The initializer list, which comes after the colon, says that, right, then the size private member is going to take the value n, and data is now going to have a new, so it's going to generate a pointer to a double, and these brackets means this is a C-style array, so we're going to get a new pointer to a double array, which is of length size. Okay, and that's quite sensible. So I've now got an array of doubles which has the length of the size that's being stored in this array. Great. In the explicit constructor, and then the deep constructor, when we hit the end of the lifetime, calls delete, okay, on this array data. And then we have a way to access this. We're going to get a reference to the double stored with the square brackets as an operator to get access. If we pass an unsigned int into the square brackets, so that's I being passed in, we're going to return the data at that location. That's reasonably sensible. Now, there's no bounds checking here or anything like this, which is a bit worrying because we could just ask something at the end or things like that. But that's kind of an initial implementation. But you can see how there's a memory resource being allocated with a constructor, deallocated with a destructor. Okay. Yeah, so I wanted to show you the example here. So type this up. It's effectively doing exactly the same thing. Let me just do something here quickly. I'll come on to this in a moment. So above, we have exactly the code that we've just discussed. Okay, again, array, size, data are the members. And all I've added is an explicit constructor is I've added a print statement. And in the destructor, I've added a print statement. So that when they're called, you can see it happening. Okay. And then we have some main function, main called some void, and it's going to return an int, which is going to just return 0. And I'm going to have some arbitrary length of n equals 3. And I'm going to fill all the values by accessing them using our square bracket operator and filling them just with I, and then I'm going to print them. Okay. To build that and run it. Okay, and you can see that we create the object, the constructor is called, we fill it up with things, and we print those values out as we did in the code. When we reach the end of the scope and we return, we call the destructor and the object is destroyed. Okay, but the memory that we've allocated during that period is carefully managed and is released on destruction. So that is if we use that print statement. And this is quite a nice little test to do to go around yourselves and get to fully understand the different constructors and stuff that you're adding, is just by adding a print statement into them and just seeing what comes back. Because it will be called multiple times and you can clearly identify it. Okay, when you value assign an object in C++, this will only be valid if there's a copy constructor or a copy assignment operator. Okay, so I will look at that example again. I will add in an example of doing copy instructions. So, let's just talk through this first. So, the copy constructor, when you create a new object that has the destination. So, this is direct initialization, copy initialization. So, I've got a new array Z, and it's going to take the same value as X. Okay. The assignment is when you assign a new value to an existing object. Okay. So here, X is already initialized, and then we are going to pass in. We're going to change it and make it something a new. That's going to be my array 2000, for example. Okay, so if we have my array A is equal to X, and we recompile, okay, we got an error. And there's some double free detected, okay? So why is that? So the compiler will automatically generate operations for us if all the data members of your class are copyable. So what went wrong with that example I've just shown, where it's given us an error trying to do this, because all I've done is copy something. Well, a pointer is just a number, so it can be copied implicitly. This means that the compiler tries to do it for you. It knows what it's doing about making a copy of a pointer, so it will generate the code necessary for you. And then it tries to delete it twice because it's copied the pointer. So we've called the destructor once when object X goes out of scope, and then it tries to call, and that means that the pointer and the object it's pointing to is deleted. But when we then call the Z goes out of scope, it tries to delete the same thing because it's pointing to the same object because it's just copied the address over. Okay, and you get this double deletion, and that's causes an error. So if we want to copy our array, then we need to either copy the data, okay, do a deep copy, share the data, or share the data and somehow keep track of when the last reference to it is destroyed. Okay, a shallow copy, but by default, this is not what we're doing. Okay. Of course, you can also control how your object are copied yourself by adding in some form of adding in the two types of constructors you need. The copy constructor, and the copy assignment operator by hand. So here we have copy construction. You can tell, so it's my array and it's going to return it as a reference to an operator, it's copy assignment. My array, which is the same name as the constructor, but passing in another copy of this is going to do copy construction. And we can explicitly then define a particular way we're going to copy the data. It's not defined here, it's just saying this comment's just a placeholder for how that's actually going to be done. But at least the size is taking it, so when the other here in the copy constructor is a constant reference to the thing we're going to copy from, why the square brackets up? I think that's so it deletes it as an array, so it doesn't just delete it as the integer. I'd have to look up and double check. We're then using this to say, right, we're going to initialize, so we're going to use this as a constructor, we're going to initialize size, the local data member, based on the size as size of the other, because we're doing construction by copy. And then we're also going to take data and say that's going to be equal to a new, it's going to be a new double of size. Now size has been initialized. It is not equal to the pointer for the other, which is the mistake that was just made. And therefore we need to somehow copy the data over from the other dot data. So the data member of the other myArray class, and copy the data over somehow. And you can define how you do this. A simple example would just be some form of loop, okay, to go through all the elements. Separately, we can have copy assignment. So I'm going to return a reference to a myArray, and this operator is expected on the right hand side to see a version of myArray, and we're going to call this other. We delete, because in assignment we have data and we're initialized already, so we're going to delete our own data, and we're going to delete that pointer and say that's gone. We're going to overwrite size with the value of the other size, and we're going to make a new, again, we're going to make a new pointer of double and of length size. And then we're going to copy the data. And then we are going to return the dereference to this pointer. So this is pointing to our current version of this object. We're going to dereference it and return it. So we pass this object back. And that's going to be our new value. Okay, and then the destructor exists just as the same before, and that's how you would set up in this example copy construction and copy assignment. Okay. So the other thing you might think about is that returning a value from a function looks a lot like copying. So when a function returns a value, you might think it will copy it to the target. Okay. So here we have, as an example, we have a main function which is just an the data, we're going to have some value data, it's an automatic type, it's going to take whatever read data returns. Read data is going to return a vector of ints, and it's going to return, and that's going to be answer. Okay, it's going to read some data from somewhere. So does it copy answer, or does it do something else? Okay, because answer goes out of scope when it hits the end of this this curly brace. So since C++11, the languages support the concept of moving objects from objects which the compiler knows or the programmer asserts that will not be used anymore, which means that once it knows we're not going to use this, can we move the resource around? All right. Examples are temporaries, the result of a function call or constructor expression, automatic variables that are going out of scope, the results of calling standard move on an object, okay? The destination object steals the contained resources from the source object and sets the source object into a valid but undefined state, okay? It's perfectly happy, so the source object is perfectly happy to still sit there, but there's no definition about what that state has to be, okay? Typically, the only operations you can perform on a moved from object, so the source object, are destruction and assignment. So you could reassign it with some new values. You could do copy assignment to it and still use it, or you can destroy it. Okay. So in this case, looking at our array example, you can again we're kind of so the comment here is C asterisk tools is just constructors and copy assignment, and also the destructor that we had before in our last example. We're just saying they're still in this function, we're just not repeating them here for brevity. And now we've got two new constructors. And they're constructors because, sorry, one new constructor and one new operator. First one's a constructor because it's called myArray, and it takes a forwarding reference of other. So this is double ampersand. So we can retain its consonants and other properties. And we are going to move its resources. So this is the distinction here. Like before, we had size, and we initialized it with the initializer list to the right here, the size of other. But this time we're also directly taking the data from other. Okay, so we're taking, this is a pointer, we're now taking the pointer from other. And we are setting other to something valid, but undefined. So we can set the size to 0, and we can set the other, the thing we're stealing resources from, data member, to a null pointer. It's perfectly valid, but it's undefined to use, okay? And it's ready to be used by something else or deleted. Copy assignment, move assignment operator here. Again, we have an other, and this time we need standard swap to swap the resources between the two. So that will do pretty much the same thing in this case, but you can imagine you may want other behavior in here for this. But this means you move resources between two objects, which is different from copying the resources from a different object. Okay, this is more memory efficient, except for example. But then it leaves that other operator in some undefined state. Okay? Right. So these are important idioms within sort of object orientation. So the rule of 5 says that if you define or delete one of the following, the copy constructor, the copy assignment operator, the move constructor, the move assignment operator, or the destructor, then you should probably do so for all 5. Okay? You either want all of them or none of them within your objects. 0 says that unless your class is the class solely deals with the ownership, deals with ownership, then it should be define none of the 5 special functions. So you should have, this really is a corollary of the general software engineering principle of single responsibility. You should split your code into a resource manager with all 5 functions, and a user class that has none of them, but uses the resource manager as one or more of its data members. Okay, so something's going to own the resource and have that responsibility, and something's going to use that resource through its manager. Okay, and therefore you have single responsibility of the resource. Okay. That said, the standard library does contain some helpers here in the form of some special, what's called smart pointers. Okay. So we have unique pointer is a pointer that uniquely owns the object or objects it points to. Pointers can be moved but not copied. So this is achieved by the copy constructor and the copy assign operator being deleted. So this means that the pointer can be moved around, but you can't duplicate it, therefore it's unique. Okay, and that's a special property. So I'm not going to go through this example, but this is just to give you a use case for a unique pointer. So say I have some class image. Sorry, the other thing I meant to say is that these pointers are within the library memory. So you could have a class image which has a constructor image which takes a string, so just the name of a file, and we have a unique pointer to an image, an instance of the image, and that is returned from a function called readImage. So I'm going to make a new object called image, which is the result of readImage, and readImage is going to call standard make unique, which generates a unique pointer of this type from file name. And this means that then in the main function, I just have an image pointer that's returned from readImage. When we call make unique, it calls the constructor of image and pass anything within the standard brackets to the constructor. Okay, so make unique doesn't have a constructor itself, but what it's doing is it's passing the list of arguments you need for the constructor of the type you pass it, image, so that it can start to build up and initialize image correctly and return the correct unique pointer. Image pointer is now a unique pointer to this given image, and there in this case is cats.jpg, and therefore that can be used, and you're sure that's not going to be copied, because that can be quite useful to use. And in this case, so what we're talking about here is, if we have if we want to use pointers, there's several ways to use them. So we're just expanding on the example we've just discussed. So we've got a unique pointer, and then we've also what we could do is have a reference, and we would to an object, and we would dereference the pointer to get the reference, and this would be called image ref. And now if the image class had two member functions called x and y, which would be quite reasonable if we wanted the dimensions of our image, for example, we can then, from the reference of the object that's being pointed to, we can call the functions, okay, just directly. Another way to do this, removing a line, is to just dereference the pointer rather than directly call the functions on that dereference in each case. That's a little bit more self-contained, but not the most readable. So there is a separate arrow functionality which says it's basically saying, instead of the dot, it says go dereference this pointer and then find me and call this particular function. Okay, it's quite a common syntax you'll see to dereference pointers and access members of the objects they point to. So just keep that in mind. Okay. So we've talked about unique pointers, but another option is a shared pointer. So you may want to share an object between multiple users, and that is standard shared pointer. This keeps a count of how many pointers are alive, increasing the count on a copy and decreasing it on destruction, so that you always have a count of the shared pointers that are still active. Sorry, the resources, people who are looking at this resource, or objects that are looking at this resource, are tracked in effect, not particularly which resource is doing it, but the number of them that are still alive. So an example here might be if we have in main, we can make a shared pointer on some big object. We may not want to duplicate this, so we want it to be shared, and then we can call some functions using that shared object now, which we're going to have a shared pointer to. I don't have to do any copying of it, but I can share the pointer to the object instead. Prefer unique pointers unless you really need to share. A couple of little caveats now. So sometimes you want to get a shared pointer to an object wants to get a shared pointer to itself. There is functionality to do this, but it's a little bit fun. You just have to make sure that the shared pointer has been made before calling share from this. So you have these. You're saying that this class widget is going to be a child of inherit from this public functionality. Enable shared from this of widget. It's going to have a member that's called shared pointer. It's going to return a shared pointer called self, and then it's going to return the shared pointer returned from that. It's going to then call on returning shared pointer shared from this. Okay, and these are all standard. These are functions you can find in CPP-ref. But the important thing is that you must ensure that the shared pointer has been made before calling shared from this. Otherwise, it won't work. Again, shared pointer is a little bit complicated, and I'd say steer away from them unless you have a definite use case. The other issue you can get with in this is you can have cyclical references in effect. So in this example, we have a class called cowboy, and it has a pointer. It's using pointer, which is a shared pointer of cowboy. It's got a string, it's got a name, and it's got a shared pointer cowboy, which is called partner. So it's expecting a shared pointer from somewhere else as well. So we can initialize its name, we can call the destructor when it's going to be deleted, and we can then also have a friend function that calls partner up. So that means that each of the partners, if it's called, is going to get the shared pointer of each other. Okay, and when you if I find my computer working. Okay. So here we have cowboy, and in the destructor we print names out. Okay. In the main function we're going to make two versions of this, one called Alice and one called Bob, and we're going to get them to partner up. That's all we're going to ask them to do. And then when they end main, they're going to exit their scope, and they should call their destructor. Okay. But if I take my example here, exactly the same code we just discussed, which I've compiled. And the important thing here is the destructor, when it's being called, should call delete and print out the name of the object's being deleted. If I run test, I don't get anything, which means we have some cyclical reference, okay, inside because of our shared pointers, and that can be quite dangerous. So you just have to be careful about not having cyclical references to things if you're going to use shared pointers as well. Okay. So now, despite having mentioned some bad points about pointers and the fact they can be a bit dangerous and that you need to be careful, there are some valid uses in function interfaces. A function can perfectly well accept a raw pointer as long as it doesn't want to change the lifetime of an object that is pointed to. So pointers will point to an address, okay, is the key point, and that address, the object that lives at that address, the pointer knows nothing about its lifetime. And assuming that it still exists later on or in anything is not valid, is not a good assumption. And it may mean that you point to something that's no longer there or has changed. Raw pointers do not own resources. Use a smart pointer if you want ownership. raw pointers represent a single object. Okay, use a span for contiguous range of objects. So there are some values, but smart pointers, if you want to make sure you have an understanding of ownership as well. Okay, other resources. So we mainly talked about memory because that's the one that comes up, and it's kind of the key example. But for example, files. So if we compare Python to C++ here, so in Python we might have with open a particular file name as f. So f is the open file descriptor. We can then read f into some data, something called data, and then the file is closed on exiting the block. Okay. In C++, we might have some standard string data, and we might read some file stream, and we might pass the information in using this bitewise operator into data from the file. Okay. You can also have resource allocation is initialization for files to make sure that when we go out of scope, our file is cleaned up correctly and is closed. So in this example, we have a class called file. It has a private member, which is a unique pointer of type standard file. And we call it handle, and it's initialized, set as a null pointer if we don't initialize it. So we have a default constructor, and we also have a constructor if we pass in a string, which is going to be the file name. And we also have a mode, which is going to be a character, which is going to be a descriptor of how we're going to read the file. We can then generate a handle, which will be a unique pointer, which we're going to take the value from. So we're going to give handle the value, the output of fopen, which is going to be a pointer, and this is going to be pass. Make sure that the file name is a C-style string, and we're going to pass the mode in. Then the resource we've got access to, the open file, is maintained as a unique pointer throughout the lifetime of this object file. And then if at the end of the scope, if handle is still active, then we're going to close the file. Okay. And that means that we can then have read and write members as part of this object to manipulate that file handle, but it makes sure that when it goes out of scope, it's deleted. And then this is just an example of for a file called data.dat. And we're just going to call it read. We're just going to read it using R. Okay, right. Now, with 15 minutes remaining of what we planned sort of time for today, we're going to look at the Morton ordering example, which I'm just going to bring up in a separate window, and we can discuss that before people take a look at it. I will be around until 4:30 and probably a little bit afterwards to answer any questions today, but we will review the answers to it tomorrow, simply because this can take a little bit of time, and I want to make sure people get the opportunity to think about it properly if they do after we've got time planned for today. So let me just stop sharing my screen for a moment. Okay. Good. So, okay, this, the git clone is slightly wrong, but this is just ARCHER2 -lowercase cpp. Okay, it's the one you've been using for the other exercises. You would have already pulled this down if you've run it earlier. The key kind of thing we're looking at here is this concept of Morton ordering or Z ordering for matrix layouts. Sorry, of a matrix that lays out elements along a recursive Z-shaped curve, as shown in this figure. Okay, and this is the idea of this is meant to optimize your access pattern for data. And what this means is you'll go along and then you'll jump up a layer, but you'll continue across, and this can grow and grow and grow. And it's meant to mean that you can optimize, it should be slightly optimized for cache hierarchies where you want to access things as close to the cache hierarchy without having to tune parameters, and it should give you a good enough initial optimization of performance. Okay, but this is going to look at accessing different elements in some odd ordering. Okay, so you can compute the Z index from an X and Y indices. So say we've just got a square with 4 elements in the X and Y. So these are going to be the I and J indices respective by interleaving their bits, for an example shown here. So if I have the table, if I'm at 0, 0, it's 0. If I'm at 0, 1, it's 1. If I'm at 1, 0, it's 2. Therefore, I can start to swiggle round my bits. Okay, the mapping between X and Y indices and more indices for a 4x4 matrix is done in binary like this. So you start taking different indices and placing them in different locations. So here you have the rightmost index is 0, and the rightmost index of here is then 1. Then you take the leftmost index and place it here, leftmost index. And you can figure this out for yourself, and I would take some time just to think about this, hence why I want to set this example at the end of today in case you have some time to look at it after the session. The point of this exercise is while this is important, there's a set of helper functions for you to deal with a lot of this encoding. What we're more interested in is understanding the concepts of iterators and also resource allocation type things that we've been discussing today. So the advantage of laying out data in this way is it improves the data locality, hence cache use, without having to tune block sizes or similar parameters on a modern multi-level machine with like numer hierarchies, like 3 layers of caches, all this other stuff. Okay, you want something that's relatively gives you a good enough to start with approach. This might be that way, the way to do it. So we're going to walk through a simple implementation. So we're in the example files, we've included in the bit twiddling bits for translating between the X and Y dimensions and this binary representation, and the mores and indices in the file bits.hpp. So those functions are there for you. You don't need to worry too much about the specific implementation of the bit twiddling. They're reasonably fast, but if you're really interested, you can probably try and beat them. So in what follows, each subdirectory has the same number. So we've got step 1, there's a step 1 subdirectory. So using the partial implementation in matrix.hpp, your task is to implement the allocation and release of memory to store the data to use and to use the helper function in bits.hpp to allow element access. We need to implement a number of member functions marked in the source code with to-dos in comments, and add whatever data members are needed marked in the same way. Okay, there's a test program that will run to sanity check your implementation, and there's a make file provided so you can run make. Okay. There's also step 2 is to implement an iterator yourself. So we had a question earlier around, can you implement your own iterators and why might this be useful? If you want to write some non-linear access pattern, but it's got a defined algorithm, you can define an iterator that does this for you, that can increment in an interesting way. And if that gives you optimal performance because you're able to access data in a more local manner, that's why you might be interested in iterators. Okay. So there is there's a partial solution to part 1 in part 2, but try to go about it yourselves initially. So the exercise in part 2 is to complete the matrix iterator class template that's been started. Most of the boilerplate has been provided, so that's the sort of class structure and the like. You want to have this work as a bidirectional iterator. So that means you need a direction, and there's a reference and CPP reference provided for bidirectional iterators. And have a read up there before you get into too much detail there. And again, you need to look at the section marked with to-dos. Okay. So this all can be found at this location for the example. Okay, I'm going to be around for the next 20 minutes or so to answer any questions people have on this example, but I suggest for the remaining time people have a go, and then we'll go through the results tomorrow morning when we start at 9:30 for the first session tomorrow. Any other questions before we move on? Okay, if people need to run off, by all means, feel free to go now. I'm not going to cover any more content today, but if you want to get support as you start looking at this exercise, me and Jeffrey will be here for another, so I'll be here for another 20 minutes or so till sort of quarter.